The fuel that rocket engines combust can't just be any explosive chemical. A lot of thought is put into the fuel. In order to better understand fuel, two terms must be understood first. One of those terms is delta V. Delta V means total potential change in velocity. In science, the delta symbol means a change in, and the V stands for velocity. The other important term is specific impulse. Specific impulse is a measure of the efficiency of a rocket engine. It is usually measured as the number of seconds a rocket engine can fire with 9.8 newtons of thrust and 1 kilogram of propellant. There are several other equations for specific impulse. One equation states that specific impulse is proportional to the square root of chamber temperature divided by the average molecular mass. This happens because temperature is a measure of the kinetic energy that is being applied to each individual molecule in the chamber, accelerating them at a rate equal to the net force applied divided by the mass of the molecule. Another equation states that specific impulse is equal to pounds of thrust divided by pounds of propellant consumed per second. A third equation says that specific impulse is equal to the exhaust velocity divided by gravity. This tells us that in order to maximize specific impulse, a fuel that combusts with high energy and has low molecular mass is desirable. But specific impulse is not the only consideration when picking rocket fuels. Another equation also states that delta V is roughly proportional to bulk propellant density. Because of these two factors, a high density propellant with high combustion energy and low molecular mass is most desirable when picking a propellant. Rockets use many different kinds of fuel. The most common fuels are hydrogen, RP1, and methane. However, those fuels cannot combust on their own, so most rockets add liquid oxygen or LOX to the mix. Hydrogen is a great propellant. It burns incredibly hot and has the lowest molecular mass of any molecule, although it doesn't have the highest density. Another advantage of hydrogen is the environmental effects. Hydrogen combusts with LOX into a substance commonly known as water, which is not bad when released into the atmosphere. Hydrogen can also be a renewable resource because it can be electrolyzed from water, although it is most commonly produced from methane. Then you might be asking yourself, if hydrogen is so great, why use RP1? First of all, what is RP1? RP1 stands for Rocket Propellant 1, and it is effectively a highly refined version of diesel. This means that it is liquid at room temperature, so you do not need to cool it, while hydrogen has to be cooled to negative 253 degrees Celsius or 20 degrees Kelvin, which is just barely above absolute zero. RP1 is also great because it has a much higher density than hydrogen. Hydrogen tanks have to be significantly larger than RP1 tanks because of hydrogen's low density. RP1 also has a higher molecular mass than hydrogen, which probably stems from the fact that its chemical formula is C10H14O4, so RP1 has a lower specific impulse than hydrogen. On the other hand, methane, or CH4, is in between hydrogen and RP1 for everything. It has a good molecular mass, medium density, and a high boiling point of negative 161.6 degrees Celsius, which is higher than oxygen's negative 183 degrees Celsius. One problem that all of those fuels have is ignition. They all require a separate entity to light them. For example, on the Russian Soyuz, what is functionally a giant match is stuck into the engines to light them. But that is only used on the Soyuz. Most rockets use a mixture of triethylaluminum and triethylborane, or TTAB, which is a substance that will explode on contact with oxygen. The U.S. Space Shuttle used a different ignition method. In the RS-25, prior to engine ignition, a small quantity of LOX and hydrogen was diverted into a separate chamber that had a spark plug that would ignite the hydrogen and LOX to create a mini blowtorch in the engine and ignite the rest of the propellant. But that is all necessary if you just use hypergolic propellant. Hypergolic propellants are two propellants that will explode on contact with each other. In fact, the previously mentioned TTAB is hypergolic with LOX. Hypergolic propellants might seem like the best choice, but they are not. Hypergolic propellants generally have suboptimal combustions, have high molecular mass, and have OK density, which is why they are not commonly used as fuels. A common problem with rockets is their lack of specific impulse. Even the most efficient hydrogen and LOX engine can only achieve a maximum sea level specific impulse of 389.3 seconds, which is terrible considering that most jet engines achieve specific impulses in the thousands. The efficiency of rocket engines can be improved by adding metal to the fuel. Some metals have low molecular mass, high energy combustion, and high density. NASA has done research into the potential usage of beryllium, lithium, and aluminum in rockets. Beryllium has a higher density than Rp1, high energy combustion, and a low molecular mass due to its positioning on the periodic table. This makes it a perfect third propellant to add to a hydrogen and oxygen system. When added to a hydrogen and oxygen system, the specific impulse at sea level can be increased to 458.5 seconds. But beryllium is not a good candidate due to its very high toxicity. Lithium, on the other hand, has a lower molecular mass than beryllium and a high energy combustion, but has a low density. This cancels out any potential benefits of adding lithium to its system. Finally, aluminum has a super high energy combustion and an ultra high density, but has a high molecular weight. When aluminum is added to a hydrogen and oxygen system, the specific impulse only increases by 6.1 seconds, but the delta V greatly increases because of the high density. This means that aluminum is the only real candidate for a third propellant. Tripropellants, of course, come with their own unique problems. Because very high sustained temperatures are required to combust metals, ignition and combustion can pose a challenge. In order to attain the required temperatures, normal propellants must be combusted without metal while the temperatures reach their peak. Another problem is actually getting the metal into the combustion chamber. Metals are usually not liquids and cannot be pumped, so a gel of some kind that contains grounded metal would need to be used in order to get the metal to flow like a liquid. Another problem is that the heat produced by the metal combusting is much too high for traditional metal alloys to withstand, so new chambers that can survive high temperatures would have to be designed.